One of the crucial aspects of working with joint random variables is this notion of dependence or independence between the two. And in this case, we're talking about stochastic independence. Yes, there is a relationship between stochastic independence and whether there's a functional or mathematical dependence or independence at work. And we'll get into more of that in the next lesson when we start talking about covariance and correlation and what these terms mean and whether independence implies correlation or not and vice versa. Right? But the bigger, larger scale question here is, are our two random variables independent? And for these discrete random variables that we've looked at so far, this is a fairly straightforward kind of evaluation. If they are independent, then it has to be true that the joint probability of x equaling one specific value and y equaling another specific value must be equal to the product of the marginals. And that has to be true for all combinations of the individual values. Right? And the way you get to this, remember we have that the joint is equal to the conditional times the marginal, or we can swap the roles there, right? And in the case of the conditional, if you have independence, then x given y is going to just equal the marginal for two independent ones. And it just says that telling me something about y tells me nothing statistically speaking or probabilistically speaking about the likelihood of x, if the two are stochastically independent. And certainly if there's a functional dependence, you would expect that that wouldn't be true, right? And certainly in our case for the traffic counter, we would think that there would be dependence between the actual number of vehicles and the recorded. And indeed, we'd like there to be a perfect relationship between the two, a one-to-one kind of relationship, but the imperfect nature means that there's some randomness that's getting thrown in there. Right, so we wouldn't expect there to be independence in that specific case, but how would we demonstrate that it actually does happen that way? And let's go back to that one specific situation where we had an actual number of two vehicles that arrived in a 30-second interval, and we had one recorded, so there was an error. So here's a case of imperfection. And from our data, we found that the probability mass for this specific case of x equaling 2 and y equaling 1 happened 12 out of those 400 times, and that's a frequency of 0.03 or 3% of the time. We also, if you take a look back at that data, had for the marginal for x that we had two vehicles arrive 80 out of the 400 times, or about 20% of the time. From the marginal of y, we had only one vehicle recorded 160 out of those 400 times, or 40% of the time. Right, so in this case, the product of the marginals for the specific case, px times py, is equal to 0.2 times 0.4, or 0.08. And that is not, of course, equal to the joint, and therefore that's enough alone. We only have to have this happen once to demonstrate that x and y are stochastically dependent. Some people say statistically dependent, and some people drop off the adjective entirely and just say, well, they're dependent. And again, this is what we expect to be the case in this particular example, and we would hope that they would be dependent, else we really have no accuracy in this particular instrument. A useful result, because it says that's not a valid instrument to measure something. And again, just to emphasize this here, the equality that we're seeking in that calculation, as in this one right here, that the joint has to be equal to the product of the marginals, right? This equality right up here must be true for all combinations of our two random variables in order for them to be independent. Find one example. So it's a lot easier to demonstrate dependency than there is independency if you're doing this processing by hand. But of course you have a computer that can manipulate that for a whole lot of multiple variables.